So I guess everyone can listen to me and hear me.
Yes.
Okay. So welcome to the PNS on hardware software co-design. This is the second lecture on virtual memory basics. We're going to discuss some basic concepts of virtual memory. And my name is Konstantinos Kanellopoulos, and this is a course from offered by Safari at PTES Zurich. So let's see first how memory is organized and structured in today's systems, and what does the programmer see. So the programmer is writing applications that use store instructions, that we store something in memory cells, and it's using also load instructions. And so far, in a simplistic way, we assume that the whole memory is physical. Like we can immediately write at any point and load from any point in the physical memory. But that's not the ideal memory, right? Because the way we define ideal memory is like a zero access time memory. We have zero latency. We can go super fast to memory. We can assume that it has infinite capacity. And this is one of the key benefits of using virtual memory, as we will discuss later. And it also has zero cost and infinite bandwidth. In this lecture, we're going to focus on the infinite capacity. So let's take a look at today's abstractions, virtual versus physical memory. So the programmer sees only a virtual memory. He doesn't have any access to the physical memory. And this way, he can assume that the memory is infinite. But the reality is the following, that the physical memory size is much smaller than what the programmer assumes. And the reason we do that is because we do not want to offload to the programmer the management of the physical memory, because this is really complex and it makes his life extremely hard. So the system software, along with the hardware, cooperatively, they map virtual memory addresses to physical memory. In this way, the system automatically manages the physical memory space transparently to the programmer. So the programmer does not need to handle where to place pages in the physical memory. It just uses the virtual addresses, and underneath, the system manages the physical memory space. So the programmer does not need to know the physical size of the memory nor manage it. And a small physical memory can appear as a huge one to the programmer, and his life is much easier. He doesn't need to care about like how to allocate, how to place data inside the memory. However, downside is that we have a more complex system software and a more complex architecture, because we need to do everything transparently using a runtime. So this is a classic example of the programmer microarchitect trade-off. We make the life of the programmer much easier, but we make the life of the system maintainer, the system designer, and the microarchitect much harder. So let's take a look at the benefits of automatic management of memory. So first, programmer does not need to deal with any physical addresses. Second, each process has its own independent mapping of virtual to physical addresses. And this enables code and data to be located anywhere in physical memory. So relocation, we can achieve relocation and flexible location of data. So let me give you the following example. If we go back to the example where the programmer assumes that the memory is always physical, and the programmer needs to place right now its code and the data, but the programmer needs to handle this on its own. Like he needs to be able to say, okay, I'm going to place my code here and my data here. But if some other programmer as well wants to place his code and his data in the same place, then we have a problem, right? And the question is, how does programmer manage all these things? The second, which I also mentioned, is the isolation and separation of code and data of different processes in physical memory. Let's say we have two different processes, right? Process A and process B. And what we want to do is we want to use the same physical location. So both processes want to use the same physical location. How does the system understand that, okay, process A wants to use physical location 0 and process B wants to use physical location 0, but they should not do that because their data should be isolated or separated. And that's what automatic management of memory enables, this type of separation and isolation. Yes, and it also, the automatic memory management enables efficient code and data sharing between multiple processes. Using this runtime system, the virtual memory, we are able to say, okay, both the virtual addresses of these two processes will point to the same physical location. If we do not have the concept of virtual memory, we just use physical memories, we somehow need to keep track of which pointer should point to the same physical location. That is not easy. So let me give you an example with a physical memory only. So this, the physical memory only computers were in the beginning the Cray supercomputers or early personal computers and many older embedded systems. And as you can see here, the CPU loads data from memory or stores data in memory using only physical addresses. So we're generating, the program generates physical memory addresses. But this is obsolete right now. This doesn't happen in most of the systems that we use nowadays. And what is the problem? So the problem is that physical memory is of limited size. And the question is, what will the programmer do if he needs more memory? So should the programmer be concerned about the size of data blocks that fitting in the physical memory? So let's say the programmer wants to allocate more than 1 gigabyte, more than the size of the physical memory, let's say, which is 1 gigabyte. What will happen in this case? So should the programmer also manage the data movement from the disk to memory? So if we use more memory than the physical memory device, then should also the programmer write some type of handlers that move data from disk to memory? So this is a big issue that virtual memory is able to handle. Second, multiple programs may need the physical memory. So should the programmer make sure all the processes can fit in the physical memory? That's not possible. Should also the programmer ensure that two processes do not unintentionally or incorrectly use the same physical memory portion? As I said before, let's say that we have two programs and the way they are written, they both access the same physical locations for different data. That is wrong, that's incorrect. So the programmer should write some type of should write this application in a way to avoid this. And of course, like current ISAs can support address spaces larger than the physical memory size, which means that we have, for example, in today's systems, we have 64-bit address spaces with byte addressability, and we might use physical or virtual addresses which are much larger than the size of the physical memory device. So the question is, what if you do not have enough physical memory again? So let's talk about some difficulties of direct physical addressing. First, as we said before, programmer needs to manage the physical memory space, which is inconvenient and difficult. And this becomes even more difficult when you have multiple processes running in the same processor. It's also difficult to support code and data relocation. So addresses are directly specified in the program. So how do you know where to place the code and the data? That's a hard thing to do for the programmer. It's also difficult to support multiple processes. So protection and isolation between multiple processes is essential in today's systems. And we need, as I said before, to make sure that we do not have unintentional or incorrect behavior from the different processes. We should be able also to share physical memory without problems. Yeah, and the direct physical addressing also makes it really difficult to support data and code sharing across processes. So and this is due to the fact that different processes need to reference the same physical address, and they need to synchronize or communicate somehow about the usage of physical addresses. So what is virtual memory? So the key idea here in virtual memory, which is a really old concept, it's one of the oldest concepts in computer architecture, and it I think has remained for the last maybe 40 or 30 years. So the idea is to give each program the illusion of a large address space while having a small physical memory. This way, the programmer does not need to worry about managing the physical memory within a process or across processes. So the programmer can assume that they have an infinite amount of physical memory. And hardware and software cooperatively and automatically manage the physical memory space to provide the illusion that's meant to provide this illusion. And the illusion is maintained for each independent process. Let's see the basic mechanism. So the basic mechanism in indirection, right? So we do not access directly the physical memory. We first access indirectly, we first access the virtual memory, and then we indirectly, using a mapping, we access the physical memory. So the address generated by the program, by instruction of the program, is a virtual address. It's not it is not the physical address used to address the main memory. It is not a real address, the virtual address. It's just an abstraction, it's a concept. So this is also called linear address in the x86 ISA. So the address translation mechanism maps this address. There is a mapping between the virtual address and the physical address space, the physical address. And these are called real addresses in x86. And this is correct, like I like this terminology, real address. Real address is like, it's the actual address in the physical device. That's why it's called in the ISA real address. And there is an address translation mechanism which can be implemented in hardware, software, or in a hardware-software cooperative way. So let's see a conceptual view of virtual memory. So we have the illusion of a large separate address space per process. As you can see on the left, we have process 1 with a virtual address space 1, and on the right, we can see process 2, virtual address space 2. As you can see, we have one virtual page per process, the gray part here. And as you can see, even though they have the same virtual page number, it starts from 0, they point to different physical pages. And that's the key concept in virtual memory. This way, we have the same virtual addresses that point out to different physical pages. And this happens using a mapping, which I will describe in the next slides. So this process of address translation, it requires an indirection in the mapping between the virtual and the physical address space. So let's describe what is the virtual page and the virtual address space, what is physical frame. So the virtual address space is divided into pages. You can imagine pages as chunks, like as we partition the virtual address space into statically sized chunks. And the same thing we do with the physical address space, and we partition into frames. So you can think of it in an analogy as the same way partition a cache into cache blocks. So a virtual page is mapped to a physical frame if the page is in physical memory, or a location in the disk otherwise. And even accessed virtual page is not in memory, but on the disk. The virtual memory system brings the page into the physical frame and adjusts the mapping. And this is called demand paging. This is what most of the systems nowadays are using, the demand paging. What I want to mention here is that the process of bringing the page into the physical frame and adjusting the mapping is called page fault, which I will discuss in the later slides. And the page table is the table that stores the mapping of virtual pages to physical frames. Let's see the example here. We have the CPU. The CPU uses virtual addresses. The virtual addresses are used to access the page table, and the page table let us know, okay, does my virtual page locate in memory or in the disk? So as you can see here in the example, we have two virtual pages that sit in the disk, reside in the disk, and two virtual pages that reside in the physical memory. So the hardware essentially converts virtual addresses into physical addresses via an OS-managed lookup table, which is the page table. Let's see a more concrete example here. So we have two processes with a 4 GB large virtual address spaces, and we have a physical address space, a physical memory that is 16 megabytes. And as you can see here, we partition each one of these spaces into pages and frames respectively. We have two virtual pages in the two processes and one physical page in the physical address space. And as you can see, we create a mapping between the virtual pages and the physical pages in the device. Let's talk about 4 key issues in indirection and mapping. So first, when do we need to map a virtual page to a physical address? Like when do we need to allocate a page essentially? When does the virtual address is referenced by the program for the first time? Second, what is the mapping granularity? Like how do we partition this page? Like how large is this partitioning? How large are these chunks, the page size and the frame size? So the mapping granularity in today's systems support multiple granularities. We use 3 different page sizes, and we will discuss this later. The third question is where and how to store the virtual to physical mappings. So the operating system should handle this. The hardware should handle this. It should be cooperative. We'll see in the next slides. And another important question is, what do we do when the physical address space is full? So we somehow need to evict some unlikely to be needed virtual address from the physical memory and send it back to the disk. So essentially, the physical memory, in other words, it works as a cache. The physical memory is a cache of the disk. It's a cache for pages stored on the disk, and it's essentially a fully associative cache in modern systems, as a virtual page can potentially be mapped to any physical frame. And this is it offers high flexibility because we can map essentially each virtual page into in any place in physical memory. So we have discussed in the DDCA course similar caching issues with the caches, like where and how to find a page in cache, which pages to remove, how large, small should be the page size, and what do we do in the case of dirty pages. Let's see an analogy between cache and virtual memory definitions. So with cache, we use the term block, the cache block. In virtual memory, we use the term page. Each block has a size. In cache, we call it block size. In virtual memory, we call it page size. The cache has a block offset. We access some part of the block, some part of the cache block. We also access some part of the page. Every time we miss in the cache, we handle the cache miss. Every time we miss in the virtual memory, we don't find the data in the physical memory, we have a page fault. And the index, the tag we're using in the cache, is the equivalent of the virtual page number we're using in the virtual memory. Let's take a look at some more virtual memory definitions. What is the page size? As I discussed before, the mapping is the mapping granularity of virtual to physical address spaces. It dictates also how much the amount of data transferred from the hard disk to the DRAM at once. The page table is a table that stores the virtual to physical page mappings. It's essentially a lookup table that is used to translate virtual pages to physical frames. Like we have a virtual page address and we want to find out what's the corresponding physical frame address. Another translation is the process of determining the physical address from the virtual address, which in today's systems happens directly in hardware. Let's see a simple example, I would say, of address translation. So on the top, you can see we have a virtual address with 31 bits. And as you can see, we have you have a page offset of 12 bits. This means that we have a page size of 4 kilobytes. So we do not need to translate this page offset because this is internal to each one of the pages, right? So what we need to translate is from bits 30 to bits 12, and we need to translate the VPN into a physical page number. So we perform the address translation process. We look up the page table to find out the corresponding physical page number from the virtual page number. Let's see another example. So we have a system, let's say, with where each process has a 2 GB large virtual address space. So the virtual address space is 2 to the power of 31 bytes. But we have a physical memory size of 128 megabytes. This is 2 to the power of 27 bytes. And the page size is 4 kilobytes, which is 2 to the power of 12 bytes. We need 12 bits for the last 12 bits that represent the page and the page offset. So how do we organize this? We have a virtual address that uses 31 bits. We have a physical address that requires 27 bits, a page offset that's 12 bits. And how many virtual pages do we have? 2 to the 31 divided by 2 to the power of 12, which is 2 to the power of 19. So for the virtual page number, we use 19 bits. How many physical pages do we have? We have 2 to the power of 27 divided by 2 to the power of 12. I repeat again, 2 to the power of 12 is the size of the page. So we have 2 to the power of 15 physical pages, which means that we need to translate from 19 bits of virtual page and to 15 bits of physical page. So the question is, how do we translate the addresses? We translate the addresses using the page table, which is again the lookup table that contains the mapping between the virtual pages to the physical pages. And the page table has an entry for each virtual page. So in each page table entry has the validity bit, which checks whether the virtual page is located in the physical memory or not. If not, it must be fetched from the hard disk. And it also contains the physical page number. The physical page number gives us information about the location of the virtual page in the physical memory. We also have more information in each page table entry about what replacement policy will follow, whether the page has been dirty or modified, what are the permission, the access bits, the data protection, which we'll discuss later. You can see an example of a page table here. As you can see, we have the validity bit on the left and the physical page number in each one of the entries that are valid. So as you can see here, we need to locate the page table in the physical memory. So the page table is always stored in the physical memory, and it can be accessed using a page table based register that points to the beginning of the table. As you can see here, it points at the first entry. So let's say that we want to translate right now the virtual address 247C. So what we do is we use the virtual page number, which is number 2, to access and index the page table. And we find out that the entry that corresponds to the virtual page number 2 is valid, which means that the data is in physical memory. And it corresponds to the physical page number 7FFF. So we access the page table, we find the entry, and the page table provides the physical page number. And the page offset bits do not need to change during translation, because after we find out the physical page number, we use the last 12 bits, which is the 47C, to access internally the data in the page. So let's see another example here. And the question is, what is the physical address of the virtual address 5F20? So what we need to do first is find the page table entry containing the translation for the corresponding virtual page number. And then we look up the PTE, the page table entry at this address. How do we do that? The general formula is page table base register plus virtual page number multiplied by the page table entry size, which in our case is 1 bit plus, it depends on the ISA, but it can be 64 bits per physical page number, which means 65 bits in total. So the virtual page number in this scenario is 5, and the page offset is F20. So we go to the to this entry. The virtual page number corresponds to this entry in the page table, and we find out that in the 5th entry, the physical page that corresponds to this virtual page number 5 is the physical page 1. Let's see another example. And let's say that in this scenario, we have used the physical address 730. So in this scenario, the virtual page number is 7. But as we can see, when we access the page table, the entry 7 is invalid. And this means that the page does not reside in the physical memory. And what we need to do right now is we need to swap the virtual page into the physical memory from the disk. We need to find the position of the virtual page in the disk and fetch it into the physical memory. That, as we said, works as a cache for the pages that reside in the disk. One issue with the current with this page table size design is that we need to support. Imagine that we need to support 64-bit virtual addresses and 40-bit physical addresses. And the question is, how large is this page table? And as you can see, it's extremely large, and that is just for one process, 2 to the power of 54 bytes. Just for one process, which is impossible to store. And imagine that the process might not be using the entire VM space, and it just needs to allocate 2 to the power of 54 bytes, which makes it extremely expensive and really hard to use. So the first challenge with the page table is that it's large. The page table is really large. And at least part of it needs to be located in physical memory for the pages that have been allocated in the physical memory. And the solution to this problem is what today's systems are using as a page table, which are some multi-level hierarchical page tables, which are coming from a data structure called radix tree. Let's discuss about the multi-level page table. So the idea here is to organize page table in a hierarchical manner, such that only a small first level page table has to be in physical memory. We do not need to store all the page table entries because multiple virtual memory pages are not being used by the application. So we're using multi-level hierarchical page tables. And as you can see here, we have two levels of two levels of page table. At the first level, we access it using the first 9 bits of the virtual address plus the page table register. And then we find a pointer to the second level of the page table. But if an entry in the first level of the page table is not valid, this means that we do not need to point to the second level page table and we do not need to allocate it. And this saves important storage and capacity. And this way we make the page table, we design the page table in a more feasible way. So in today's systems, as I said before, we're using a multi-level page table. And as you can see here, we're using the page table number, which is the first 9 bits, plus the page table register. We access the first entry in the first level page table, and we find out that we need to go to the to the physical address 2375000, and we combine it with the page table offset, the other 9 bits, the next 10 bits, of the virtual address, and we find out the final physical page number, which is 23F1, and we combine it with the page offset to find the physical address that corresponds to the virtual address. If anyone has any questions on this, we can, of course, discuss the example. So imagine that for an n-level page table, we need n page table accesses to find the page table entry. In this scenario, with a 2-level page table, we need 2 page table accesses to find the page table entry. This is an example from an early x86 architecture where we were using 4 kilobyte pages. There were 2 levels of page table, one called the page directory, which is the first level, and the second one, which is the actual page table that holds the page table entries. The CR3 register is a page directory based register, and this is controlled by the operating system. The operating system sets this register so that the hardware knows where is this page directory in the physical memory. And it's important that there is no other way to access the page table. We need the CR3 register to find out where exactly is the page table located in the physical memory. As you can see here, this is the same example. This is from the Intel manual. I don't think we need to go deeper into this. And this is the 4-level paging in x86 64. So this is a 64-bit processors. Again, this is from the Intel's manual. And as you can see here, we're not using 2 levels of page table. We're using 4 levels of page table. And it is important to understand why, because we found out that 2 levels were not enough. We needed more levels because with the existing ISA and the 64-bit virtual addresses and the 50-bit physical addresses, we were not able to maintain a low storage page table using 2 levels of page table. So we needed 4 levels of page table, which is increasing as a number. In the next generation processors, there will be 5 levels of page table. So as we said, the first challenge is that the page table is large, and the solution to that is the multi-level hierarchical page tables. And in the next lecture, we're going to discuss about some overheads of the accessing the hierarchical page tables. The second challenge is that each instruction, fetch, load, or store, requires at least 2 memory accesses. One for the address translation, we need to read the page table, and another one to access the data using the physical address after the translation. So we see also data flow dependency here. We need to first perform the address translation, and then using the physical address as a result of the address translation, we access the data in the physical memory using the physical address. So we need 2 memory accesses to service an instruction fetch or a load store, which greatly degrades execution time. As I said, we have a dependency as well. It's not just that we need to perform the access. we depend on this access because we need to discover the physical address before we access the physical memory. And as I said before, the number of accesses depend on the number of levels of the page table. In the current architecture, we're using 4-level page tables, which means that we need to perform 4 accesses to perform the address translation. In today's systems, 4 accesses will be too much. So there are many different techniques which are used to reduce these 4 accesses to even 1 or 0. So this is not really clever, performing 4 accesses for each address translation step. So we need a way to speed up the translation. So how does address translation happen? How do we obtain the physical address from a virtual address? The page size is specified in the ISA. For example, in the VAX, it was 512 bytes. And today we're using 4 kilobyte, 2 megabyte, or 1 gigabyte pages. So we have a small and large pages mixed together. We're going to discuss about different page sizes in the next lecture into more detail, because there are trade-offs in using different page sizes and enabling different page sizes in the system. And the page table contains an entry, as we discussed before, for each one of the virtual pages. The page table, this is called the page table entry, or PTE, which is essentially the last level of the page table. And the last level of the page table is the tag store. The page table is essentially the tag store for the physical memory data store. I repeat again, it's a mapping between the virtual memory and the physical memory. And the PTE is the tag store entry for a virtual page in memory. So we have a validity bit to indicate the validity presence in the physical memory. We need tag bits, which is the physical page numbers. And we need the physical page number, the physical frame number or page is the same thing, to support the translation. We need bits to support the replacement. We need to find out which pages need to be replaced, same way as we did with LRUs and caches. We need a dirty bit to support write-back caching. If a page has been written and it's dirty, and we need to evict it from physical memory, we need to write it back to disk. If it is not written, then and dirty, we do not need to write it back to the disk. We also need protection bits to enable access controller protection, because as I will discuss later, virtual memory does not only enable automatic memory management and the idea of an infinite memory, it also enables access protection. These are two decoupled concepts, but in today's systems, we're using it in one. Virtual memory supports both. So how do we support right now virtual memory? Where do all these things run? Is it running in software? Is it running in hardware? Is it running in the operating system? Where does the address translation happen? Who decides about the page size? Who handles memory allocations? These are all valid questions, and we need to find out how to support virtual memory in today's system. So virtual memory requires both hardware and software support. The page table, as I said before, is stored in memory, and it is controlled by the operating system. The operating system updates the page table. But we use in today's hardware specialized hardware structures called translation look-aside buffers to accelerate the translation. And I will discuss a lot on this in the next lecture. The hardware components that contains the translation look-aside buffers, it's called the memory management unit. And every core has one memory management unit to perform the address translation. So the memory management unit contains multiple components. The page table registers, the CR3 register. Where is the page table? We need to answer this question using the MMU. Where is this page table? Do I have the translation already in the TLBs, in the translation look-aside buffers? If I miss, how do I walk the page table? How do I perform the page table access? The page table walk and page table access is the same concept. We use both words interchangeably. So it is the job of the software to leverage the MMU to populate the page tables and decide what to replace in the physical memory. And we need to change the page table register on every context switch. So imagine I run one process with a page table X, and I need to switch to another process B, with a page table Y. So whenever I switch to another process, I need to communicate to the MMU the content of the new CR3 register, the content of the new page table register that points to another page table. We also may need to make sure that we handle page faults and ensure the correct mapping. And right now we'll go deeper into what is a page fault. A page fault is a miss in the physical memory. So if a page does not reside in the physical memory, then it resides in the disk, we access the page table entry, and it indicates that the virtual page is not in the main memory. So where is it? It's in the disk. So every time this happens in hardware, we need to trigger a page fault exception. That's how it's called. And the OS trap handler, the page fault exception handler, is invoked to move data from the disk into memory. So in today's systems, to give you a brief understanding, the MMU, the hardware component, tells the operating system, okay, the data do not reside in the main memory, and you need to fetch it for me from the disk. So the program stalls and the operating system takes place. It executes in the same core to service the page fault. Other processes can continue executing, but not the process that suffers from the page fault. And the operating system right now has full control over the placement of the data. So before the fault, as you can see, we have 2 pages residing in the main memory, 2 pages residing in the disk. And for the page that caused the page fault, we map it, we bring it from the disk into the physical memory. And right now we have 3 pages that reside in the physical memory and 1 in the disk. How do we service a page fault? First, the processor signals a controller to handle the page fault. So we read a block of length P starting at address X and store starting at a memory address Y. And this way we do this to fetch it from the disk to the main memory. So a disk to mem read occurs, and this doesn't involve the processor. We have a component called the direct memory access component that handles this transfer. This is called DMA transfer. And an IO controller is managing this DMA. So the controller signals a completion, the processor is interrupted, and the OS resumes the suspended process. When the DMA finishes, which means that the data have been moved to the main memory, we continue executing the program. So the question is, what happens if the physical memory is full? Let's say that we have a list, we are this example here, and we didn't have space to move the page from the disk back to the physical memory. What would happen in this case? So if the physical memory is full, we need to replace some physical frame in the case of a page fault. For example, can we perform true LRU? We're not sure, because we might have a 4 GB memory with 4 KB pages, which makes it probably extremely expensive to have a true LRU. And modern systems use approximations of the least recently used policy. One example is the clock algorithm. I will not go deeper into that. They also use more sophisticated algorithms to take into account the frequency of use of each page. This is called the ARC algorithm, as described in this paper from FAST 2003. So let's see an analogy between the cache versus the page replacement. So physical memory, DRAM, is a cache for the disk. So it's managed by the system software via the virtual memory subsystem. And the page replacement, as you can think of it, is like similar to the cache replacement problem. The page table is the tag store for the physical memory data store. And the difference, but there are some key differences. First, we do not access the cache and the physical memory with the same speed. We do not have the same number of blocks in the cache and the physical memory. And when we want to find the replacement candidate in the physical memory, we have much higher tolerance in the amount of time we need to spend finding it, which means the following. So imagine we are in the cache, right? And we need to find out, okay, which cache block should we evict? So this is an algorithm, this is a process that should run fast, because we are in the microarchitecture, in the core microarchitecture, we need to decide quickly about the replacement policy. However, in the case of the cache of the page fault, where we need to find a replacement for the replacement physical frame, then we have much more time to decide about which page we need to evict. And this happens because the disk access is much more expensive than the memory access. To give you a rough understanding, to access the main memory, we need, let's say, hundreds of nanoseconds, but accessing the disk requires access times at the order of milliseconds, not nanoseconds. And one other important parameter is the role of hardware versus software. Caches in modern processors, DL1 cache and DL2 cache and DL3 cache, are purely hardware managed. However, the replacement candidates here in the case of a page fault are not hardware managed. The operating system decides which page it will evict from the physical memory and which page it will and how you will bring a page from the disk, which makes the system much more complicated, of course, the system software, but which gives us much more flexibility. Another key concept enabled by virtual memory is memory protection. So multiple programs in today's systems processes run at once, and each process has its own page table. So each process can use the entire virtual address space without worrying about where other programs are. And a process can only access the physical pages mapped in its page table. It should not be able to overwrite memory or read memory of another process. Virtual memory provides protection and isolation between processes and enables access control mechanisms per page. We extend each page table entry, we extend the page table with additional information to enable access control mechanisms. So as you can see here, the page table is per process. So each process has its own virtual address space. And as you can see, we see the full address space for each program. And this way we simplify memory allocation, sharing, linking, and loading as I described before. But the two different virtual address spaces should not interfere with each other. The virtual page one should not be able to access, the process one should not be able to access physical pages that belong to another program. So we enable access and protection control via the virtual memory. And we do that at the page level granularity. So not every process is allowed to access every page. For example, we may need supervisor level privilege to access system pages. A user space application should not be able to access the supervisor level privileged pages. So the idea is to store access control information on a page basis in the process's page table. We extend the page table with access control bits, access control information per page table entry. And this way we enforce access control at the same time as translation. We discover the physical page number, we also discover the protection bits. So in today's systems, the virtual memory system serves two functions. First, the address translation to give the illusion of the large physical memory, automatic memory management. We enable sharing, we enable transparent updates to the processor, transparent updates to the program. And we also enable access control. We are able to protect the data of each process. Yeah, as you can see, this is a schematic drawn by Professor Mutlu. When we translate the address and we at the same time perform the access control. And the PTE, the page table entry, contains both the access control bits and the physical frame number to perform the translation. So we extend the page table entries with permission bits, and we check the bits on each access and during a page fault. And if violated, we generate an exception, which is an access protection exception. As you have seen, many of you in applications that you have written, you have it in some cases, a segmentation fault. Segmentation fault happens exactly because of that. The process one, for example, is does not have right access to the physical address 6. And this way, when it's trying to perform a write to the physical page 6, we have a segmentation fault because we do not have permissions to write to the physical page 6. And we can, of course, enforce different privilege levels as in x86. We have different protection rings, the applications, operating system services, operating system kernel, and many others. So there are 4 privileges in the x86, which we refer as rings. The highest privilege, ring 0, which is the operating system, and the ring 3, which is the lowest privilege, which is the user applications. Ring 1 and 2 are not really used. Rings 0, 1, and 2 are essentially the supervisor, and ring 3 is the user space application. So as you can see, we have in the x86, we're using the page directory and the page table entry, 32 bits for each one of them. And the PDE, as I discussed before, contains a pointer to the next level, to the page table entry. And it also contains flags. So the PDE contains protection bits, not per page right now. It contains per 4 megabyte pages. And we have two granularities of protection. We have protection at the 4 megabyte granularity. We also have protection at the 4 kilobyte granularity. So if we do not, for example, in this scenario, if we perform an access to the page table and we find out that we don't have access to the 4 megabyte page, not 4 kilobyte, 4 megabyte page, then we do not even perform the access to the PTE because we do not have access to this page. And if we have access to this 4 megabyte page, then we need to find out if we have access to the internal 4 kilobyte page that we're trying to access, right? And that's why we check also the flags of the page table entry. So using the PDE's flags, we protect at once all 1024 pages in the page table. And using the PTE's flags, we protect one page at a time. We protect one 4 kilobyte page at a time. So you can imagine this as a hierarchical protection scheme. At the first level, we protect a larger page block. And at the next level, we only protect one page. We store protection bits for one page. So there are three major issues in today's virtual memory. First, how large is the page table and how do we store and access it? How can we speed up translation and access control check, which I will discuss in the next lecture. And when do we do the translation in relation to the cache access? So essentially this means how can we accelerate others' translation, how we can accelerate the access control, and how do we do all this in hardware? Because that's where we should do it. That's the fastest way of doing it. And there are many issues which we'll not cover in detail in this lecture. What happens in a context switch? How can you handle multiple page sizes, etc. So issue number one, how large is the page table and where do we store it? Do we store it in hardware? Do we store it in physical memory? Do we store it in virtual memory? As we discussed before, we store it, all today's systems store it in the physical memory. How can we store the page table without requiring physical memory that can store all the page tables? And as we discussed in the previous slides, the idea is to use multi-level page tables. Only the first level page table has to be in physical memory, and the remaining levels can be either in physical or virtual memory, but just cast in the physical memory when accessed. How do we access the page table? As I said, in the x86, we access using the CR3 register and the base limit register. And if the VPN, the virtual page number, is out of bounds, it exceeds the page table base register, then the process did not allocate the virtual page, which is an access control exception. The page table base register is also part of the process's context. We need to store it for each process so that we can load it back in the case of a context switch. So you can see here an example of the page table. This is again from the Intel manual, and this is we discussed about. This is how do we access the different the page tables. I will give a really concrete example next time, so I will not go deep into that right now. And I will ask two questions, then I will conclude my talk. So first is how can we speed up the translation and access control check? And this is one really important question where many researchers have focused on, and there are multiple research proposals coming from the group and other groups on this topic. And the main question is how fast is others translation? Because as I said, there is a data flow dependency. We first need to perform the others translation to discover the physical address, and then we access the caches and the main memory. So how can we make the address translation fast? As I described before, we have this hardware structure called Memory Management Unit that accelerates the address translation. So I will finish with this slide. So the evolution of hardware support for the virtual memory is the following along the year. So in earlier days, we had a memory management unit that contains an L1 data translation look-aside buffer. It's a small cache that contains some recent translations, and an L1 instruction translation look-aside buffer. And whenever we're missing these, it means that we need to perform a page table access. We need to access the page table. So in the earlier days, the programs were trapping back to the operating system, and the operating system was running a program that accessed the page table to find out the translation. But throughout the years, this has changed dramatically. And right now we have, in the modern address translation pipeline, we have multiple components that are essential towards accelerating the address translation process. And this way, we are able to perform fast address translation, fast data protection lookups, and make the performance and enhance the performance of the applications. So this is I will conclude my talk. Thanks everyone for attending this talk, and have a good day.
Thanks, Konstantinos.
Rahul, can you stop the live stream?
Yeah, sure.